Bismillahirrahmanirrahim. Today I wanted to talk about some right angle theorems, 5 of them specifically, and next time inshallah we shall elaborate on these and use them in some proofs. They're reasonably easy enough and straightforward to understand, but we have to understand and memorize them inshallah. Before we talk about these theorems, we have to review a few concepts that we have already covered. So we talked about, for example, properties of equality for real numbers. And this is very important because, as you can see, these recur in different concepts. And here we had properties of equality for real numbers. And then we had similarly properties of congruent segments. All right, so let me get my pen over here. Now, as you can see, properties of congruent segments, we had reflexive, symmetric, and transitive property of congruent segments. From these, if you wanted to, you can derive some of these, but we kind of keep this 3 the most commonly used properties of congruent segments, and we can always fall back onto the properties of equality of real numbers when we are working with segments, angles, etc., the remainder of the properties. So these properties of equality for real numbers becomes particularly important for that reason, because you can always fall back onto with other such as segments and angles, etc. Because property of addition property of equality, for example, applies not only for real numbers but also for measures of angles, measures of segments, etc. because those measures are taken in real numbers. So these are important. These also, in other words, these also carry on to other concepts like this, except that we always convert them into real numbers and then use the properties of equality for real numbers. So we talked about the addition, subtraction, multiplication, division, reflexive, symmetric, transitive property of real numbers, a substitution property of real numbers, and the distributive property of real numbers. And I have suggested to you before that you should be able to articulate all of these in the if-then conditional statement form. So the multiplication property of equality for real numbers, for example, would state if A equals B, then A times C equals B times C, like that. And then properties of congruent segment, for example, the transitive property of congruent segment states that if segment AB is congruent to segment CD and segment CD is congruent to segment EF, then segment AB is congruent to segment EF. Those all you should know and be able to articulate. So to this we had also added the properties of congruent angles, and these were RST, reflexive, symmetric, and transitive property of congruent angles. So we had properties of congruent segments and properties of congruent angles that we had talked about previously. And then we talked about some postulates and theorems as it relates to angles. If you recall, the segment addition postulate was bedrock of postulates, for so to speak, and it stated that basically that if it allowed basically to add 2 baby segments to give us 1 big segment. That is, if the A, B, and C are collinear, we could add the baby segments to give us B segments, and that would be equal to the measure of AC here. And that would only happen if these are collinear, and this is a biconditional statement, and that's if and only if. Similarly, angle addition postulate is also a biconditional statement. That means it is the original conditional statements and its converse are true. And in this case, D is in the interior of angle ABC if and only if the measure of 2 baby angles will give the 1 big angle. This allowed us to add angles to give bigger angles, and that was the angle addition postulate. So segment addition postulate has its cousin, the angle addition postulate. And then we learned some theorems. This is the linear pair theorem. That is, if 2 angles form a linear pair, then they are supplementary. If 2 angles form a linear pair, then they are supplementary. The definition of a linear pair is that, in fact, that there are 2 angles whose non-shared side is opposite rays. So that's the actual definition of linear pair. So this angle 1 and 2 have a shared side here, and then they have a non-shared side. The non-shared side of angle 1 and 2 are opposite rays, and that's the definition of a linear pair. Nevertheless, if 2 angles form a linear pair, then they are supplementary. That's a theorem. Then they had the complementary adjacent angles theorem. So these are adjacent angles and they're complementary. And we suggested if the non-common sides, if the non-shared sides, if the non-common sides of two adjacent angles form a right angle, so the non-common side, that's this side and this side, those are the two non-common sides of a two adjacent angles. If they form a right angle, then these angles, angle 1 and 2, are complementary. So this is a complementary adjacent angle theorem. So we had the linear pair theorem. If two angles form a linear pair, then they are supplementary. And then the complementary adjacent angle theorem. If the non-common sides of two adjacent angles form a right angle, then they are complementary. Now these names over here, like the linear pair theorem and the complementary adjacent angle theorem, there you can come up with whatever name one likes to remember these. Those are actually my affectionate name for these theorems, and some different books have different names for these theorems. The names themselves are not important, as you know. The actual phrasing of the theorem itself is very important. And then to today's subject, right angle theorems. These theorems that we're going to talk about next are very important and very useful, and they're reasonably easy to appreciate and memorize, I think, inshallah. So before we begin those theorems, before we appreciate those theorems, we have to simply understand the definition of perpendicularity. So what does it mean for two line segments raised to be perpendicular? So we have to know the definition of perpendicularity. So definition of perpendicularity is simply lines, rays, or segments that intersect at right angles. Now remember, lines can be perpendicular, two rays can be perpendicular, as we had the complementary adjacent angle theorem. Lines can be perpendicular, rays can be perpendicular, or segments can be perpendicular, right? So lines, rays, and segments can be perpendicular. So the definition of perpendicularity is that lines, rays, or segments that they intersect at right angles. If they intersect at right angles, so here's one ray, here's another ray. If they can intersect at right angles, or I can have lines that can intersect at right angles like this, and you can have segments that intersect at right angles like this. So here's one segment, here's another segment like this. And they all, so lines, rays, and segments can all intersect at right angles. They are perpendicular if they intersect at right angles. So that's the definition of perpendicularity. Now observe that there's this symbol and there's this symbol. This symbol means right angle. Sometimes you just write this, which kind of looks like an L. But in print it looks easier to differentiate this from an L. But in when you're writing with your hand, I always put a little like right angle symbol over here. So this symbol means right angles, and this symbol means perpendicular. So you have to differentiate between this symbol right here, which means right angle, and this symbol, which means perpendicular. Okay, so you can say angle 1 is a right angle. Okay, that's how you would read that. Angle 1 is a right angle. Okay, or you can say line L is perpendicular to line M. So that's how you would read that. So this symbol means right angle, and this symbol means perpendicular. All right, so here's the first of our theorems, the first three of the theorems, and there's a diagram that goes with this. Now, the first theorem says perpendicular lines intersect to form four right angles. I call this affectionately the four right angles theorem. That's the four right angle theorems. So if you have two perpendicular lines, like line L and line M over here, they intersect to form four right angles. Here's 1, here's 2, here's 3, and here's 4. Okay, so perpendicular lines intersect to form four right angles. So this is very important because in many questions, the questions will say, for example, line L and line M are perpendicular lines, and from that we can say angle 1 and angle 2 are right angles. How do you know? Because of this theorem. Perpendicular lines intersect to form four right angles. So this theorem basically gives us that anytime you have two perpendicular lines, you get as a gift four right angles, so to speak. So this is four right angles theorem. Okay, that's easy enough. Perpendicular lines intersect to form four right angles. And then this is very important. All right angles are congruent. This is kind of like the theorem that we had before, which we proved, in fact, that all vertical angles are congruent. So we had a theorem before that said all vertical angles are congruent. Here we have a theorem that states that all right angles are congruent. And these are all theorems that are pretty easy to prove, which we shall inshallah elaborate upon next time. So all right angles are congruent, just like all vertical angles are congruent. And the third theorem for today is that perpendicular lines form congruent adjacent angles. That's pretty easy enough. That's like almost saying this and this, right? So perpendicular lines form congruent adjacent angles. So 1 and 2 are congruent, 1 and 3 are congruent, 3 and 4 are congruent, and 2 and 4 are congruent. So perpendicular lines form congruent adjacent angles. So now that's pretty intuitive and easy, right? But of these theorems, we'll use some of them more often than others. Okay, this is obviously, you can imagine how common you use this theorem. All right angles are congruent, and then this theorem is particularly important because we'll use this a lot. So and this is, of course, we'll use it a lot, but it is pretty intuitive. Perpendicular lines intersect to form 4 right angles. So that's a very important theorem to remember, because it kind of gives us 4 right angles if anytime you're given 2 perpendicular lines. Here it says line L is perpendicular to line M. And third, perpendicular lines form congruent adjacent angles. Okay, so if you forgot this one, see, then you can easily derive this from all right angles are congruent type of thing, right? So one step removed from this. So if you know one, sometimes you can derive the other. So that's why the first 2 here, I believe, are particularly important to appreciate. And then we have 2 additional theorems here. I'm going to add this here. The fourth theorem for the day is this one right here. If 2 angles are supplementary, then they are if 2 angles are congruent, if 2 congruent angles are supplementary, then they are right angles. So if 2 congruent angles are supplementary, so here's angle 1, here's angle 2, they're congruent to each other. That's what those little symbol means over here, that they're congruent, right? Little symbol here. So angle 1 is congruent to angle 2, and they are supplementary. If two congruent angles are supplementary, then they are right. They have to be right. If they're supplementary and they're 90, and there's that they add up to 180 degrees, and they're congruent, each one of them has to be 90 degrees like this, correct? So if 2 congruent angles are supplementary, then they are right angles. If 2 congruent angles are supplementary, then they are right angles. If 2 congruent angles are supplementary, then they are right angles. All right. And finally, the last theorem that we have for today is this one over here. If 2 congruent angles form a linear pair, then they are right angles. That's easy enough too, right? Because linear pair, meaning they they kind of make a line together like this, but then they're congruent, right? So if they're congruent, they form a linear pair. They have to be 90 degrees. Now the last 2 theorems, in a way, they're saying the same thing, but you can be supplementary without being a linear pair, right? For example, over here, these 2 angles are supplementary without being a linear pair. In other words, these 2 theorems apply to supplementary angles. This one applies to adjacent supplementary angles, the second one, and this one applies to non-adjacent supplementary angles, right? So they're saying very similar things, but for different circumstances. So again, if 2 congruent angles are supplementary, if 2 congruent angles are supplementary, then they are right angles. And if 2 congruent angles form a linear pair, then they are right angles. These are all right angle theorems. So before we finish, let's go over all of these, and inshallah request you to memorize these so they become very natural to you. The first theorem that we learn is perpendicular lines intersect to form 4 right angles. This is the 4 right angles theorem. That's my affectionate terminology for this theorem. Perpendicular lines intersect to form 4 right angles. All right angles are congruent. perpendicular lines form congruent adjacent angles. Congruent adjacent angles. If two congruent angles are supplementary, then they are right angles. If two congruent angles form a linear pair, then they are right angles. Again, perpendicular lines intersect to form 4 right angles. All right angles are congruent. Perpendicular lines form congruent adjacent angles. If two congruent angles are supplementary, then they are right angles. If two congruent angles form a linear pair, then they are right angles. Inshallah, we shall develop on this next time. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.